what if I gave you an equation? This equation, dy dx, so the derivative of y with respect to x, is 2x. And I asked you to find an equation for y in terms of x. Okay, so we're given the derivative, and we're asked to find the equation for y. So you know how to do this. We're trying to find a value of y where the derivative is 2x. And so that's just basically saying that we need the antiderivative, right? And so, so you know how to find the antiderivative of a function by integrating, right? So I'm going to show you a little bit of a trick. We can take this value, dy dx, and we can write it this way. dy is equal to 2x dx. Okay? Now we did something similar to this when we did integration by parts. So, or actually use substitution, or basic substitution is like this as well. So, and then we can integrate both sides, right? And so we end up with y on this side, and when we integrate, we're finding the indefinite integral of 2x, so basically the antiderivative, we get x squared. But we have to remember plus c, right? Because x squared is not the only function that satisfies well, I won't call it a differential equation yet. But x squared is not the only value that satisfies that equation, right? If I had x squared plus 2, or x squared plus 5, or x squared minus 70, all of those equations would satisfy this equation dy dx equals 2x. Right? So essentially you get a family of curves, right? So family of curves. All right. Well, so it's not a unique solution, but what if we wanted a unique solution? Could we find one? The only way that we can find a unique solution is to have an initial value. Okay. So for example, let's say we have this initial condition where y is equal to 7 when x is equal to 3. Okay, if we know that, then we can take our general solution up here, y equals x squared plus c, and we can find c. So we know that y is 7 when x is 3. So we're just going to substitute 7 for y and 3 for x, right, into our equation, and we'll find out what c is. So 7 is equal to 9 plus c. So if I subtract 9 from both sides, then I get c is equal to minus 2. So in this case, we can find, for this particular initial condition, we have y is equal to x squared minus 2. Okay, and when you have an initial condition, this is called a particular solution. All right. So let's take a look at another one. That one was pretty easy, right? That was something that you knew how to do. Let's take a look at another equation. Here we have, it looks very similar, right? It says dy dx is equal to 2y. Okay, so instead of 2x, we've got 2y. All right, so how do we solve this one? All right, we can't, we've got, if we try to break it up the way we did before, we would have dy is equal to 2y dx, and we don't know, y is y, right? It's not x, so we can't integrate it with respect to x unless we know what it is with respect to x. So, so right now there may be some, you might see a trick that we could do right now. But unless you're very perceptive, right now all we know how to do is guess and check. Okay, so I gotta think. Okay, I want a function that when I take the derivative of, I just get twice the function. Well, here's what I know. I know a function that when I take the derivative, that I can take the derivative of and get the same function. So I know that, oops, that if I take the derivative with respect to x of e to the x, I get e to the x. So that satisfies the equation dy dx equals y, right? So because if I had essentially y equals e to the x, then the derivative of y with respect to x is y. Okay, so that satisfies that equation. But let's think about the chain rule. So what if I, instead of making y equal to e to the x, what if I made y equal e to the 2x? Then we would have dy dx is equal to 2 e to the 2x, right? So we're using the chain rule. So the derivative of the outside would just be e to the 2x, and then we would take a times the derivative of 2x, which is just 2. Okay, and since y is equal to 2x, this is equal to 2y, right? This right here is y. So so that is a function that satisfies this equation dy dx equals 2y. So one solution, let me write this down, one solution to this equation is y equals e to the 2x. Okay, so one question you might ask though is that the only solution? And the answer to that question is no. If you have a function y equals any constant times e to the 2x, then, then dy dx equals 2c e to the 2x, right? Where again, this right here is just y. So we get again that dy dx is equal to 2y. So we can generalize it and say that y equals c e to the 2x is also a solution, right? Is also a solution. I can't write today. Solution. Gosh, I can't spell. All right, solution for any constant c. Okay. Now we still don't know, is that the only solution? Is there something else that we could do? But at least we found a couple of, well, actually this is the same solution, only c is 1, right? So we found more than one solution. That's good, but we don't know, is that still the only one? We just had to do it by guess and check. So congratulations, you have just solved your first differential equation. Well, 2 differential equations, right? The first one really was a differential equation, even though it was something that we already knew how to do. Because a differential equation is just an equation that relates functions and their derivatives. So if you ever have an equation that involves a derivative, it's a differential equation. And differential equations have different orders. A first order differential equation involves the first derivative and no higher. Second order differential equation involves the second derivative and no higher. And I suppose you could go further. A third order differential equation would involve the third derivative and no higher. All right, we're not going to go beyond second order differential equations here. In fact, we're going to focus actually on first order differential equations. But that's it. That's a differential equation, and I'll meet you for the next example.